Okay, in a moment we will have Mira and Max and Clayton come on up and solve this problem. But before they come up, I just want to review, just like 1 minute talking about yesterday's activity. Hopefully you saw a very streamlined way of solving your force problems. Every time you have a force problem, it's pretty much going to be similar to the way you did it. So they can throw all kinds of twists at you, different forces, different situations. But what you need to do is go through those steps. Remember, I didn't have an important one. Identify the object you're interested in. That's kind of an important step. But just go through those steps, and you should be able to solve them. So the last problem in the homework that's due tonight, which is not the one they're doing, as you can see, is once again taking you through those steps, having you draw the free body diagram on the computer, and then breaking your vectors into components and applying Newton's second law in each component direction, and then combine those equations to solve for the unknowns of tension 1 and tension 2. One thing, a couple students came to me just before class, and I didn't realize until they came and asked me, why is this wrong, is when you make the free body diagram on the computer, you need to make sure that you have the lengths of the forces proportionally correct. And as one student said, I can't believe you didn't see that. At the bottom left-hand corner of the screen, it tells you if the sum of the forces in the x direction and the y direction is positive, 0, or negative. So you'll need to have those both being 0 if the acceleration is 0 to get it correct, which is the case in that problem. Okay, so come on up, you three. Once again, it's Mira, Max, and Clayton. And remember this time around to explain to people what you're doing.
Someone's going to change the calculations. Okay, so oh wait, I don't have it. Do you want to do the diagram? I didn't draw a diagram for this one.
Did you try that?
No, it gives us a, wasn't there a picture?
No. Okay.
I can go grab my computer. I have it.
I know how to do the math, but I didn't draw a diagram for this particular one. So we have helicopters. This thing is spinning. I don't know how to draw this at 60. This is on the, no, there's no picture, so I'm just going to draw. There's my helicopter. So that's spinning that. And this is 8 meters long. So we have our blades that are 4.8 meters long, and it's rotating at a speed of 260 revolutions per minute. And so to calculate our centripetal acceleration, we want to use the formula of acceleration for centripetal equals RW squared.
I have to correct, that's not W, it's omega.
Omega, sorry. It's omega. And so to be able to plug in this information, we have R, which is 4.8 meters. And then to get revolutions per minute, we need to convert that to radians per second. And so that conversion is omega is equal to 260. And I am not good at writing on this screen. Per minute. It's 2 pi radians over 1 revolution, and then 1 equals 60 seconds. And that gives us
27.23.
Okay, so with that information, we can then plug it into this equation by having acceleration, centripetal acceleration is equal to 4.8 meters times 27.23 radians per second squared. And that gives us
1,000 or 17.
What?
Have we?
Don't we need for this equation? We had it as like WR squared, and then we have to divide it by R as well.
That's not.
Yeah, I did was.
Yeah, that's just this one.
Okay. Yeah.
Yeah. I don't like drawing on this thing at all. It's good. So that is part A. And then, so then I think, wait. Yes. And so, is that what you guys? Am I good doing good so far? That's just B. So, yeah. Okay, so comparing the linear speed of the tip with the speed of sound, taken to be 340 meters per second, and then give your answer in percent of the speed of sound. So this one we need to use the velocity of our speed because it's not instead of acceleration. So to find velocity, you have V equals the R, the radius, and omega. And so we have V equals 27.23 radians per second with 4.8 meters. And that will give us a velocity of
130.7
second. And then we use the formula for finding how it compares to the sound. We have velocity of the tip divided by velocity of the sound times 100 to give us the percent. And that will be
38.4.
30.7 per second divided equals what?
38.4.
Yep.
All right, that was perfect. Now, a question for everyone to think about here. If you look at her calculations, she had like radians per second times meters, and what was the unit she got in her answer?
It was a browser.
The bottom left calculation.
Did I put the wrong unit on? No, that's sweet.
Right.
Yeah.
The radians just disappeared because they're unitless. So she did it perfectly correct. The radians just, poof, they're gone because they just mean, oh, we were measuring an angle in the unitless angle. Question, Emily?
When we're working with this kind of problem, when it says it's RP, are we working in radians in our calculator?
No, when it says R, that means revolution. And so one revolution was 2 pi radians. That was her conversion, the first one she did right.
So, but when we do those conversions, are we in radians in our calculator?
The only time the units in the calculator are going to matter is when you're doing a trigonometric function, sine, cosine, tangent, one of those. Otherwise, your computer doesn't care, or calculator doesn't care. It's not going to make a difference. All right, thank you. Perfect job.
I have a question.
Go ahead.
So, whenever we're looking for like linear speed or stuff like that, is that always going to be the equation V equals RW?
The relationship between linear speed and angular speed is yes, indeed. V is equal to R omega.
So if they had asked to calculate centripetal acceleration in that one, in the first one, but then the second one, they were talking about velocity, you just know you're going to be using that one.
Because we knew omega, we used omega squared, or they used omega squared R, so they didn't have to calculate V for part A. They had to calculate V for part B, so they could have calculated V first and then used V squared over R. It would have gotten you the same place.
So when you're looking for acceleration, it's going to be the omega squared R. When you're looking for velocity, it's just going to be R and omega.
Okay, I'm going to go back because when you're finding the acceleration, you either have those are exactly equivalent because of the relationship that V is equal to omega R. So if I put V into the first one, I have omega squared R squared over R. One of the R's cancel, I have omega squared R. So they're exactly equal. There's no differentiation between them.
Yeah.
You just use whatever's convenient.
I'm saying, like, whenever you're calculating the velocity, when it comes to, like, the one down there, you're always just going to know you're going to be using that equation. I just want to make sure there's not, like, some other equation or something.
This is the equation that relates omega, the angular velocity, with V, the tangential speed.
Okay.
So if you're relating those two, it's always by this relation. All right. Maybe. We're going to talk about not about the roller coaster problem at all today. Should have changed that picture. We're going to talk about universal gravitation. But first, I did want to talk about a little thing that's going on right now. You guys know about Florence over there on the East Coast, right? It is a hurricane. Let's start with simple things. And I'm going to ask Michael just not to answer because he cares too much. He will just answer all the questions. So what's the difference between the tornadoes and the hurricanes? The what?
Magnitude.
It's not merely magnitude. I mean, there is a big difference in magnitude.
Hurricanes form over water, tornadoes over land.
Okay, hurricanes form over water, tornadoes over land is the primary differentiator. They're both cyclonic storms. They're both spinning storms. And then comes the question of what causes them. Now, the cause of a tornado is actually more complicated than the cause of a hurricane. So we're just going to talk about the hurricane. To start with the hurricane, you have to have a hot spot in the ocean. You have to have hot ocean water. Why hot ocean water? Because the air above the ocean water is heated up to a higher temperature. Higher temperature, we'll learn this soon enough, means the molecules are moving faster. As molecules move faster, they bounce off each other harder, which means they tend to separate. You can think of if we're all standing in a group, if we're going like this, we can stand really close and it wouldn't be a problem. But if we're going fast, we're going to bounce off things and everything's going to be pushed out. So that's what happens with hot air. Everything gets expanded. But that means that the density, the mass per unit volume decreases. And just like we talked about with the centrifuge, the less dense things on the outside of the centrifuge, the more dense things on the inside. The same thing occurs with the Earth's gravitation. The less dense things float up. So the hotter air floats up. So you create an upward airflow. Now, you have to have a top pressure system to go along with this for a hurricane to form. Hot water alone doesn't cause the hurricane to form. You also have to have it's a low pressure system on top of the air for it to actually form. But how does that make the spin is the question that relates to what we're talking about. And to answer that, the answer is the Coriolis effect you see up there in the corner. The Coriolis effect is something that is real, as long as you believe that the Earth is spinning, of course, and it's something that is observed. Although all of the examples I was taught when I was in college, it turns out are pretty suspect. You know, there's a story about naval war games And this most advanced system took into account the Coriolis effect, so it was super accurate. They went to the southern hemisphere and it missed by a long shot. And it was because it was deviating the wrong direction. And it turns out we can actually calculate how much the difference is. It's not significant enough to make that story. But here's what the Coriolis effect is. If you are standing at the, let's say, the equator. Now we're going to take this merry-go-round. Oh, I can't draw when I zoom in, now can I? Take the merry-go-round and treat it like we are on the equator if we're standing on the edge of that merry-go-round. If you're on the merry-go-round and the Earth is spinning, if you throw a ball toward the center of the merry-go-round, when it leaves your hand, it has a velocity that is going toward the center because you threw it toward the center. But it also has a tangential velocity because you're rotating. So when you throw the ball toward the center, so if you're standing here and you throw it toward the center, the actual velocity is going to be that velocity you gave it plus the velocity you had going around the circle. So the actual velocity is going to be something like this. Even though as far as you could see, you were throwing it toward the center. And so it's going to go off like this and never go over the center. If you were closer to the center, you would have less tangential speed because of that omega r. And so it would have less of an angle to the side. Well, how does all this make any sense in regard to the weather? If you are at the equator and you throw a ball north, that's pretty much the same idea. You're throwing it north, and as it falls back to the Earth, it's going to get closer to the axis of rotation, like it's going toward the middle of the merry-go-round. But it has that tangential velocity to the side that you have, and that's not going to change. So as you get closer to the center of the Earth is traveling at a slower tangential speed than the ball was when you threw it. Hence, the ball is traveling faster, horizontally faster than the Earth is traveling, and it'll start to move ahead of the Earth. Since the Earth is rotating toward the east, it'll move toward the east. So when you're on the equator, whether you throw it to the north or the south, the ball is going to deviate toward the east because you're traveling faster toward the east than the parts of the Earth that are not as far from the center of the Earth. So that's shown on this upper picture. Well, it's kind of shown. It's a little confusing on the picture, especially because it's showing what's happening at upper atmospheres, I believe. But you have a deviation for things that are going to a smaller radius from the Earth. Now, of course, if you have hot air rising, that's going to a larger radius from the Earth. And so that's going to have the opposite effect. It's going to be going slower than the air up there is. And so that process means that as the air rises, you're going to have a certain rotation that occurs. And a low pressure system will pull air in, and that Coriolis effect will cause the air to be deviated instead of coming straight in to the low pressure system. If you have a high pressure system and it's going out, it has a deviation again. And both of these deviations are going to cause the same net effect of rotation. So in the northern hemisphere, the rotation for your hurricanes are always going to be, I'm looking at the picture, just trying to say from that picture that's counterclockwise as viewed from above. In the southern hemisphere, it's going to be just the opposite because you're getting, opposite sides of which direction the land is going slower. So hurricanes spin the opposite direction, northern hemisphere versus southern hemisphere, and it's because of this Coriolis effect. One last thing on Coriolis effect. Anybody have any idea what I'm talking about now when I say the Coriolis effect? Okay, at least a few people. Good. It's the result of going closer or farther from the radius of the Earth, or the axis of the Earth's spin. So one thing we talk about is the direction that toilets rotate when you flush them, right? You flush it and they rotate one direction. Has anyone seen the Simpsons episode that deals with this? It's kind of funny. It's very much Bart Simpson humor. He ends up making a collect call to some guy in Australia, keeps him on the phone for like an hour, and the collect phone call becomes an international incident because of the huge telephone charges for that kid trying to explain to him what's going on with the toilet. In the end, the State Department sends Bart to Australia to try to keep them from having an international incident. And Bart's so excited he goes to the toilet in the U.S. Embassy, and they've got all this mechanism to make the water rotate the right direction. Okay. We say that it rotates the direction it does because of the Coriolis effect. And in fact, if your toilet was big enough, that would be true. But our toilets are so small, the amount of change in radius of the Earth's rotation for the water going down the toilet is so small that the effect here from the Coriolis effect is not important. If you were to take a non-biased water pail and drain it, you might have 49 times it went one direction and 51 times the other. It's really not a significant factor. But our toilets are made with the water coming out at an angle to make it so they always swirl in the direction the Coriolis effect would make them swirl, just so it's working with that small effect. Because the toilets flush more efficiently and they clean the bowl more efficiently if the water is swirling instead of just draining. How do I know they clean the bowl more efficiently? A year ago, we bought toilets in our house that don't swirl the water. Now we have to clean the toilets a lot more. So, let that be a lesson when you go toilet shopping. Coriolis effect is a cool effect that's simply the result of changing radius. Now to universal gravitation. We've talked about Isaac Newton and his very good year because of the Black Plague. Black Plague, no school, no school. He goes to his grandma's house. He was not sitting on the beach, of course. And it wasn't a cypress tree with an apple falling off of it either. There probably was no apple tree at all. That's something he used as an illustration that there is a force acting at a distance. And they said if there's a force acting at a distance on that apple, then there must be a force acting at a distance on the moon. And that led him to the idea of gravitation being a force that acts at a distance. So the force of gravity, and so now I finally officially have introduced this. I thought I had before I gave you a homework problem on it. So I used this in a homework problem. You've seen it. But now we've gotten to it officially. The force of gravity, G, which is just a constant, times the product of two masses divided by the separation of the centers of the masses squared. So if you double the separation between the two masses, what are you going to do to the force of gravity? If R doubles, remember R is the separation of the centers, what happens to the force? Gets smaller by a factor of 1/4 because you have the two squared. So we call it an inverse square force law. Now, actually, before I go on from here, I want to make sure a few things that there's like 2 or 3 questions that everyone missed on the pretest. That pretest that had to do with forces. And so this is the stuff that was on that test, the force stuff that we've been studying this week and last week. And so here's some common misconceptions. When I take a tennis ball, which I have to grab to hold in my hand as I talk about this, when I take a tennis ball and I throw it, what made it move? What?
Your hand.
My hand. Okay, my hand applied a force on it. Force is anything that pushes or pulls. So once it leaves my hand, why is it moving once it leaves my hand? Perfect kick. Yeah.
Yep.
We got this all figured out, me and Andrew. Practice before class. What's making it move once it leaves my hand?
Is your hand stop moving?
my hand is no longer applying any noticeable force. There is still that force at a distance, which is why I thought about it now. But there's no noticeable force. My hand is not making a difference to it. I can throw it in the air and I can do whatever I want with my hand. It's not affecting it. A very common misconception people have is that after it leaves my hand, the force of my hand is keeping it going. But it's not. It's just not there anymore. It's only there when it's in contact. Gravitation being an exception. Gravitation is continuing. So why does it keep traveling when it leaves my hand? Why does it keep going up? Why doesn't it instantly go down after it leaves my hand?
Because the force that was applied to it prior to it not being applied anymore is greater than that of gravity.
I can extend that to make it correct, but I want to make sure that we have a separation. Once it leaves my hand, what would its motion be if there were no forces on it? Okay, no forces.
Oh, it would move.
It would just fly through until nothing.
Okay, because I made it move, right? If I just dropped it and there was no gravity, then you'd be absolutely right. But because I threw it, it would be upward motion. It would continue with the same upward motion, not slowing or speeding up or changing direction if there was no other force on it. Because there's gravity, gravity then slows it down. So when I throw it up, why does it keep going up for a while? It has nothing to do with my hand. My hand is why it was moving up when it left my hand. That has everything to do with my hand. That's what you were saying. I had a bigger force on it than gravity, so it accelerated upward. But once it left my hand, it had inertia, which is just the propensity to stay in constant motion. But the force of gravity was changing its motion, making it slow down, stop, and come back down. So why did it continue on? Because of inertia. Why didn't it keep on forever? Because of gravity. Those ideas make sense? Those are, like I said, I think everyone in the class missed out on the pretest. So everybody came in equally misunderstanding, very common misunderstanding. That's why it was on the test. So orbits. Newton said, well, there must be a force of gravity acting on the moon, so the moon should come crashing down on our heads. Why doesn't it? It doesn't, and I was going to do this, but I realized we don't have time. It doesn't because it's moving tangentially. And so the force of gravity is making it fall, making it change direction, but it is never getting closer because the Earth is a sphere. And so as it falls, it's just changing direction without actually having a smaller radius. What do we call it if the force is simply making it change direction and not change speed? We call it motion.
Directional acceleration.
Okay, we call it a circular motion with a centripetal acceleration. And so in this, we can calculate, real quickly. I'm not going to do everything, but we can take this is now showing the moon around the Earth. The sum of the forces on the moon toward the center is equal to the mass of the moon times the centripetal acceleration. Sum of the forces is g, mass of the Earth, mass of the moon, over the radius between the moon and the Earth squared. It's equal to the mass of the moon times the speed of the moon squared over the radius moon to Earth. And so we can take this equation. I can cancel. Notice that there is, okay, that confuses me as to why the pinch sometimes is one place and one time another. We've talked about that, but at least I have it consistently writing. My key, in case anyone wonders, is I start the presentation before I start recording. That's what's making so I can write. Just so you know. Cancel those masses. Cancel one of these radii, and you see that there is a specific speed, the speed squared that it has to have to do a circular orbit. Has to do with the mass of the Earth and the separation between the moon and the Earth. So if the moon goes faster, then we're going to have a change in that equation. The radius is going to have to change. Now, just a few technicalities that I think are more interesting than things you really have to be aware of. The Earth and the Moon, the Earth is not stationary. The Earth actually moves in the orbit. So the Earth and Moon are both orbiting the center of mass of the system. But the center mass of the Earth-Moon system is within the radius of the Earth. The same is true with the Earth orbiting the Sun. The Sun moves because of the Earth. The Sun is orbiting the Earth, you can say. But they're orbiting the center of mass of the system, which is well within the Sun. So the Sun is basically doing little wiggles, just like the Earth is basically doing little wiggles because of the Moon. This is used by astronomers to try to locate other stars with moons. They look for the wiggles of the star, and then they deduce from the wiggles of the star that must mean a moon that is, traveling with this period. So that's an interesting thing to note. Can't remember what the other thing was I was going to note here. So, yes, the other thing is, funny, interesting fact, we're going to talk about tides in just a second. The Earth spinning pulls the high tides so they're not lined up like I have shown here. The high tides and low tides of the Earth are caused because the force of gravity, G(m1 m2 over r squared), it's going to be stronger if things are closer. So the water on the side of the Earth that's closer to the Moon is pulled stronger to the Moon than the average force per mass on the Earth. And so the water gets elongated toward the Moon, creating a high tide. On the other side, the water on the far side of the Earth isn't being pulled as strongly as the Earth is. And so the water bulges out there because it's not being pulled as hard. So we have two high tides at any given time on Earth. But this shows the high tides pointing toward the Earth, but the Earth is spinning. Because the Earth is spinning, we have what we call tidal friction that pulls the water forward. So the high tides lead the Moon just a little bit. But because they lead the Moon just a little bit, so I'm going to grossly exaggerate. Here's my high tides. This is going to have a forward pull on the Moon. Now you can say, but there's a backward pull here. But because it's much farther away, it's a weaker pull. So there's a net forward pull on the Moon because of the high tides that are created by the Moon's gravitation and the Earth's spin. Well, if you pull it, what's going to happen to its speed? It should increase. And so the Earth is slowly speeding up the Moon. As the Moon speeds up, it actually then goes to a higher orbit. And so the Moon is very slowly moving away from the Earth. About 1/4 of an inch a year, I think, is the number, because of energy being transferred through the tide system. Weightlessness. It's kind of funny. I just graded some homework in the astronomy class, and the students were asked to calculate the relationship or the force of gravity in the International Space Station compared to the force of gravity on Earth. Now let's just take guesses. How do you think the force of gravity on an astronaut in the International Space Station compares to the force of gravity on Earth? And of course, 3 people shouldn't answer because they're supposed to calculate that. Okay, weightless was Ryan's answer.
Way less.
Way less. Okay, way less. Way less. Way less. Does that sound reasonable? Well, how we calculate it is pretty simple. Force of gravity is G times the mass of the Earth times the mass of the person over the radius from the center of the Earth to the person squared. Now, the force of gravity, well, I'm just going to go to G rather than the force. Well, if I go to G, that's just taking away the mass of the person. So if I calculate G for the two, we have a person that's standing on the surface of the Earth, radius of the Earth. What's the radius of the Earth? Got to look it up because I don't remember. I know it's somewhere in the ballpark of 6,000 kilometers. radius of Earth is, come on phone,
At least 10.
it gives it to me in miles. Like, who would care about miles? 6,378 kilometers. So G on Earth is G mass of Earth over radius of Earth squared. G on the International Space Station is equal to G mass of Earth over radius of Earth plus the elevation. I'll put H here squared. Well, the height for the International Space Station, I think it said, well, what did it say in the problem? You remember? I think it's 400 kilometers. So if we take 400 kilometers, which is million meters, and the height is 400 kilometers or 4 times 10 to the 5th meters, and we do these calculations, G on the International Space Station divided by G on Earth is going to be, the G and the MEs are both going to cancel, and it's going to be, well, I'll write the whole thing. Whoops, that wasn't what I wanted to do. I wanted to change the pin color, and I was trying to think of a quick way to do it, and that wasn't it. So all I have to do is take those numbers, the ratio of on top 6.378 times 10 to the 6th, divide by the bottom, which would be 6.778, and square it. Where's my calculator? Yeah. 6.378 divided by 6.778. Take that number, which is 0.94. I square it, and I get 88.5%. So the person's weight in the International Space Station is 88.5% what it is on Earth. Not that much of a difference. But we say they're weightless, right? That's why I thought that's what he said. We say they're weightless. How would we say they're weightless when they actually weigh 88.5% what they do on Earth? They're floating because the space station is falling with them. So they're both continually falling, and so they feel weightless. Measuring the weight of the Earth. Henry Cavendish, I think it was Henry, did an experiment to try to determine the weight of the Earth. What he ended up finding was the constant G. And so his apparatus had 2 masses and a little mirror, and you shine a light on the mirror, and then you measure where the reflection is. That's going to allow you to determine how much you had a rotation of the big masses thing, or the little masses thing. It's on one set of balls is hanging from a torsional string, a string that acts like a spring. If you rotate a little, it has a torque to bring it back that's proportional to how much you rotate. So you can determine how big the force is by how much it rotates. And then he moved the masses from being on one side, so big mass is on the right side of the bottom one, and then he swung them around so the big mass was on the left side. And he measured how much change in force there was by how much rotation. And it was actually through that experiment that the value of G was determined. Like I said, he was trying to measure the weight of the Earth and ended up coming up with something different. So that's an important historical aspect. 3 quick things that have to do with this. Before the time of Newton, Johannes Kepler, based on the observations of Tycho Brahe, determined that planets orbit the sun in elliptical paths. The planets don't do circles around the sun, they do ellipses. An ellipse is essentially an oval. It has 2 focal points. It's a circle that's been stretched, so instead of having one center, it has 2 focal points. And the sun's at one of those focal points. His second law is that the area swept out by a planet, if you draw a line from the planet to the sun, is constant. As the area per unit time is constant. And so in that picture, you have when the planet is close, going from period A to period B, to get a lot of area, you have to have a lot of distance covered. When it's farther away, going from E to F, you have a lot less distance to have the same amount of area. So an important outcome is that means that planets travel faster when they're closer to the sun, slower when they're farther away. And then, okay, third law I didn't put up there. The third law relates the period with the distance. So we have these three laws that Kepler determined before Newton. But when Newton came along with his calculus, his three equations of motion, and his universal law of gravitation, he came up with these all in the same 1.5 year period. And together, those explain and gave us physical reasons for Kepler's laws. Now, the last thing before the problem is some practical examples of what we're learning. If you're racing, let's say you go to the go-kart track in Omaha, Joe's Karting, and you're racing out there and you want to beat your son, which I did once or twice, 1 or 2 laps he gave me overall. I blame it on my weight. One of the important things is you don't want to have to slow down very much on the corners. And usually those things are laid out that if you choose the right line, you can just keep the go-kart at full speed the entire time. But when you're coming to a curve, what you've learned, this curve here, okay, I tried to draw it, it has a radius that's about that long. Whereas the other curve, the red car, yeah, the blue car has the red line, the red car is going to have whatever color this is, has a much longer radius. What difference does that make to the race car? Having a sharp turn versus a very broad turn.
Is the broad turn, you need less traction to turn?
You need less centripetal acceleration for the same speed if you're doing the large radius turn. Now, the limiting factor here is the grip your tires have. So in practice, you can go a lot faster on path 2, and your tires will have enough grip to keep you on the track. And so, which path is a shorter distance, path 1 or path 2? Path 1 is shorter, but path 2 you can go faster. And so if you watch something like NASCAR, they'll talk about the different lines. You'll have cars in the low groove and cars in the high groove. The ones in the high groove can go faster around the corners. The ones in the low groove can't go as fast around the corners, but they have a shorter distance to travel. And so then it comes down to, how quick can you accelerate as to which one you're going to be able to do faster. So some cars will do faster in the higher groove, some will do faster in the lower groove. There's a lot of very practical physics involved there. Okay, now our problem. NASA uses the centrifuge. Went and visited. I was going to volunteer to be a test subject, but because of my hernia history, I was medically not able to. But they spin you around, you get some pretty high accelerations. And so if this cart is at 15 degrees, that is if this angle, okay, I need to change colors because that doesn't stand out. If the angle between horizontal and that cart is at 15 degrees, then what is the centripetal acceleration? So that's the problem for you to solve. No. If you knew the radius, you could find the velocity from this, but you do not need that.
Oh, yeah. Oh, we don't need that? Oh, okay. I'm writing it on
Remember, when you have an answer for your, actually, you're supposed to be at your homework groups now. Because, homework groups are going to be the ones that come and get the credit, not individuals here. So just to remind you of your homework groups, we have Michael, Leslie, Emily, and Kaylin is 1. Ryan, Lydia, and Nathan is 2. Hannah, Wes, and Sarah is 3. DJ, Madison, and James is 4. Mira, Max, and Clayton are 5. And Andrew, Trace, and Sarah, Kim are 6.
I don't just
We're only given one. And he wants us to find another number with just one.
I love the chance for credit for that.
Well, you can get the actual value.
Because the only other thing is we can find regular. Because that's the one that
Is it quick to the something? Something to do with
I'll give you one hint. The free body diagram is the key.
So I know this way, when you look at the property line, if you look at it on the side, it's so I guess this.
Wait, what's
See the little part hanging out?
Oh. Well,
It's got ladder on the left.
that's to care about.
I assume that's like a.
I think that makes sense. So we have gravity down.
What are the forces on the box?
Or it's kind of sideways, so.
It's in contact with the top. Roll the section down. And so that you through the beam.
Because of the, it's tilted. So it's how is this?
Doesn't exist. There's a force of.
Okay, our time just ended, and because we do need to respect people's time, I will simply extend this. Email me your group submission for your solution to this. Before 5 p.m. tonight, email your group submission to it. Actually, 5 p.m. is a little early because some people might have lab or something. So let's go before 10 p.m. tonight.